Hey everybody, this is Russ Altman from The Future of Everything. Space exploration and travel are topics that are always exciting and have sparked a lot of enthusiasm. Debbie Senesky researches ways to develop tiny, tough electronics that could help augment our abilities to further explore extreme environments, such as outer space. Today we're rerunning a conversation I had with Debbie back in 2017 on this topic. I'll hope you listen in and enjoy. Before we jump into this podcast, let me ask you to please rate and review it. It helps us improve and it helps spread the word about the future of everything. So when we face a new frontier, we are often faced with logistical challenges of operating in unfamiliar and you could call them harsh environments. So think about the explorers who set sail on the ocean so many years ago. They needed boats that could withstand storms, huge sea swells, and a range of temperatures beyond what they probably typically experienced in the ports from which they came. Underwater divers need to solve problems of watertight enclosures, salt-resistant materials, and high pressure. And at the same time, as we began to explore space, we needed to ensure that the rocket ships that were built could withstand the vibration during takeoff. They needed airtight seals, especially when there were astronauts or monkeys inside. They needed to have construction sufficient to operate in the very cold parts of outer space, and while at the same time being able to re-enter Earth's atmosphere and fall through it, generating incredible heat and friction, requiring heat shields and metals that, don't melt. In all these activities, we need to innovate in materials that could function and withstand the physical stresses that these harsh environments provide. And in the case of exploration involving humans, a primary goal, of course, is to protect the humans. But we also need to find ways to protect the instruments and devices that those humans might use or that might be out there being autonomous without human intervention. Of course, everybody knows that in the last 30 years, our ability to build computer-based systems using modern electronics has exploded, but most of these devices, I think, are designed to operate in relatively mild conditions. So if you've left your smartphone out in the car on a sunny day, it probably didn't do very well. I don't know if it melted, and it may well have worked after it cooled down, but when it's hot, it doesn't do so well. In addition, if you've dropped your smartphone into freezing weather, snow, ice, it also doesn't do well. So as we explore new frontiers, there's this real challenge to make our electronic devices robust and tolerant of extremes. These instruments and devices might indeed be engineered to be more robust than humans, and so they may allow us to send them into places where it's out of the question for humans, extremes of the environment. I think of deep space, and so do others, missions to other planets in our solar system or even outside our solar system, where the trips will be long and cold. So things have to work, and they have to work for a long time. Probably a lot of this will be in a vacuum. Hypersonic travel, where the pressures and forces on materials must reach tremendous magnitudes. And the inside of an engine or the inside of a nuclear reactor, where you'd like to know what's going on. You'd like to control the chemical and physical processes that are creating this tremendous energy, and so you need to know what's going on, and there's going to be electronics there, but they're not allowed to melt or explode or do all those things that would make them less useful. Now, I don't know the full extent of these challenges, nor do I know the range of environments where it would be useful to be able to withstand these conditions, but my guest today does. Dr. Debbie Senesky is an assistant professor of aeronautics and astronautics and electrical engineering at Stanford University and works on the creation of materials focusing on electronics that can operate under extreme conditions. Debbie, in a Department of Astronautics, you must be thinking about many things involving space exploration. What are the challenges, as you see it, to creating the technologies that we would need to send probes to Venus, Mercury, Mars, and beyond?
So a couple of big challenges that we face in this area is making things tiny, so making the electronics tiny or small, and also making the electronics tough as well. And you want both of those attributes to achieve a lot of the missions that NASA wants to conduct. So my group here at Stanford works on nanoelectronics for extreme harsh environments. Nano is small, And we want things to be small so we can reduce payload, reduce cost. There's often size constraints as well. We use a special class of material that enables operation in high temperature and high radiation environments. And that also helps with resilience, reliability when we're talking about sending things to Mars or Venus, right? We want these electronics to work. We want them to be reliable. And so these special materials have these robust properties. And also, because they're robust, they don't need shielding or heavy packaging. So that also helps with the payload problem.
Now, could you tell me about what are the materials that we Earthlings use? And what are the new materials? What are they made out of? Yeah. And are they a natural extension, or is it a whole new deal?
Yeah, so Earthlings used silicon. So we're here in Silicon Valley, right? Silicon is the most ubiquitous material for semiconductors, and we use that platform for electronics. Unfortunately, silicon is limited to temperatures below 250 degrees Celsius, so it really inhibits a lot of missions. And we can, again, package them and make them bulky and heavy in order to achieve certain programmatic goals. So to overcome the limitations of silicon, we look to other types of emerging technology. And in my group, we use a special class of semiconductor materials called wide band gap semiconductor materials. You can think of them as a ceramic material. They're temperature resilient, mechanically very robust. Diamond is also in that family of materials, so very hard and strong. However, these materials also need to transport electrons.
Right. You need to get electricity through the diamond, so to speak.
Exactly. So we've been looking at gallium nitride, which is another wide band gap semiconductor material, which has a high concentration of electrons. So we can actually make transistors out of this material, and these transistors can work at elevated temperatures and also within radiation-rich environments.
So now you said that silicon gets us to about 200, 250 degrees Celsius. What are your gallium? What is the limits of your new materials in terms of temperature?
Yeah, so theoretically, these materials can function above 1,000 degrees Celsius. So in the research, we have demonstrated operation up to 600 degrees C. So in my lab, we've demonstrated a 600 C, but theoretically you can get to 1,000 based on the band gap. But there's still a lot of challenges in reaching that actual limit.
Let me ask you, my temperature familiarity, kind of peters out around the temperature of boiling water, which is, as I recall, it's about 100 degrees Celsius. So can you help us put in context what's 200 degrees, what's 1,000 degrees, what's 600 degrees? Is there anything in familiar everyday life, or, I don't know, the surface of the sun, the surface of Venus? Where do we find these kinds of temperatures? The surface of an engine?
Right. So we find these temperatures on Earth. So actually in the subsurface environment of Earth, so when you think of an oil and gas well, that well bore has a temperature of around 250 degrees Celsius. Also, your automotive engine, some of the peak temperatures can get to around 1,000 degrees C, but the wall temperatures are around 300 Celsius. So as you mentioned, even outside of Earth, there are harsh conditions. So one example that's near and dear to my heart is the planet Venus, which has a surface temperature of around 480 degrees Celsius.
Okay, so this is very helpful because what I take away is that we are around objects that have this kind of temperature all the time. If I drive my car, I'm within a couple of feet of perhaps 300 to 1,000 degrees, and it would be difficult to have electronics operating there.
That's
but
right.
You and your colleagues might want to make measurements about how my engine is doing, which require it to have a sensor sitting right there.
That's right. It's all about the data, and where we we can put sensors and electronics to obtain that new type of data, and you can feed that data into your overall system. So you can feed that data to control circuitry, or you can feed that data to, a probe or, a satellite that might be communicating to a probe.
So you mentioned about going out into these harsh environments, and you said one of your favorite places is Venus. Who doesn't love Venus? Tell me about why we would want to go to Venus, and what are we going to learn there, and then how does your work contribute to what we might want to do there?
Yeah, so Venus is our neighboring planet. And what's interesting about Venus is that it's very similar to Earth in some ways. It's similar in size and mass, so the densities are actually the same. However, they're very different in some ways as well. Their climates are different. So Venus is, as I mentioned before...
I think you said 480 degrees.
Yes.
So my iPhone will not do well.
No, you don't want to send your iPhone unshielded, uncooled on the surface of Venus. So 480 degrees Celsius. Also, the ambient is high pressure, so around 90 bar, so about 90 times our atmosphere.
So if I remember 90... Help us understand what 90 bar is.
So our atmosphere is around 1 bar approximately. And so the surface of Venus is 90 times the pressure of our atmosphere. So what that means is due to the chemical constituents, so surface of Venus, or Venus is very CO2 or carbon dioxide rich. And because of the
They have a
temperature,
major global warming problem on Venus.
Exactly.
Excuse me. Please continue.
No, really. And that's part of the science. So supercritical CO2 is in the ambient. Also, there's a lot of sulfur. If you look at images of Venus, it's kind of this yellowy haze, and that's the sulfur clouds, the sulfur haze in the ambient. So it's different from Earth in many ways as well.
And then what are the kinds of experiments, or what would we like to learn about Venus? Is there a burning question, no pun intended, about Venus that those of you in aeronautics and astronautics would love to know?
Yeah, so we want to know a few things. Number one, how did this planet evolve? Right? Why does it look the way it does today? And was it Earth-like billions of years ago? And so if we can study Venus, we can study the evolution of that geology. Also, Venus does not have tectonic plates. It's a dry atmosphere. There's no water. It also doesn't have a magnetic field. So scientifically, there's a lot of interesting things to learn.
So your compass won't work.
Your compass won't work. And also, maybe there's life there. It might be counterintuitive, but there might be life forms on Venus. There are things called extremophiles, which can live in harsh environments. So who knows?
Where are we? Where is the space program in terms of sending things to Venus? Is this a to-do on the to-do list for the next couple of months or years? Are we still arguing about whether it's worth society's investment? Talk to me about a little bit about the setting in which this kind of science is taking place.
Sure. So just some of the history. So Russia is the only country that has actually sent landers to Venus. And so a little over 30 years ago, there was a lander on Venus and took the first color images of Venus. And so since then, we haven't visited Venus. And so there are many communities that are interested in sending another lander to Venus. A lot of these missions are on the conceptual stage. People are thinking about balloons that might be located in the atmosphere, and then how do you send a probe down? And think about it, these probes, they don't last long. These missions.
Yeah, it was amazing to me that the Russians were able to take pictures.
They were able to take a picture in a little over 2 hours and communicate that data.
And how long did the devices that they sent down, how long did they function?
So there are many, many missions that did not function. But some of that we learn, right? As we engineer, we learn from our mistakes and learn from our challenges. And so the last couple of missions, again, lasted about a little over 2 hours. And so they were able to take images and then transmit. There were plans to do chemical spectroscopy and things like that, but unfortunately, the systems didn't work.
So they basically figured out how to keep that probe cool enough and functioning to take one picture or so, send it back, and then it basically melted or fell apart.
Exactly.
Thus totally justifying your research program to get them to last a little bit longer. Now, I'm sure people are wondering, can people Google these photos?
Absolutely.
Because I have a huge urge now to look at the pictures from Venus.
So if you Google Venera 13.
Venera.
That's right. And Venus, you should be able to find that on a Google search.
Awesome. And so that is so far the pinnacle of human achievement on Venus.
That's right.
And your work is kind of oriented towards let's see if we can extend that, maybe even get a movie and then watch a whole day worth of does Venus have days? Does it spin around and I don't even know.
I don't. I imagine there are Venus. Every planet should have a day. It does have a slow rotation.
Yes.
It's slower.
That's why I hesitated.
I don't know. No, thank you. That's a good question. I don't know what a Venus day is in comparison to Earth, but it certainly has a day. It doesn't have a moon, though.
No moon.
No moon.
No moon for Venus.
No moon.
Which, given the whole, the whole Greek and Roman legends and mythology, you would think that Venus would have a lot of followers, but evidently she doesn't. What about other planets? Is the idea that if we can solve Venus, we can solve everything, or does each planet pose an entirely different set of technical challenges?
Yes, each planet has its own unique environment. For example, Mars, which we have a rover on Mars,
Yes.
which is remarkable, right? Mars is not as hot as Venus, but it is cold. So I think the temperatures, don't quote me, but the temperatures get down to probably negative 100 degrees Celsius or so. And so those cold temperatures can also pose challenges on our engineering systems. Also, we are interested in going beyond our solar system. So there are groups that would like to go to Alpha Centauri, and just getting there, just the distance, right? This is our nearest star system. How do we do that? What does that spacecraft or series of spacecraft look like? And so these are the things I find very interesting and yeah.
My guess is that in addition to worrying about how to keep the electronics working, power is always an issue. What are the current models for these very long trips? Are they going to be nuclear power? Are they going to be batteries that are just amazing?
Yes, a little bit of both. If you can have nuclear power, so oftentimes spacecraft will have a radioisotope on board. People are also looking at harnessing the energy from the sun. If you're in our solar
system, close enough to the sun.
Yeah, if you're close enough to the sun, then you might be able to use solar cells, right, and power your electronics if that's available to you. Also for propulsion, people are looking at using solar energy to push these spacecraft into deep orbit as well.
Amazing. And now we're going to turn our attention to the industry of space. And I don't mean just the industry in terms of companies, but also NASA and federal agencies. I assume that they're excited about the work you're doing. And tell me, when might we see some of the technologies that your lab is working on deployed in real missions that are going up in the air?
Right. So I would categorize the work in my laboratory as early stage. So at this point, we work closely with NASA to test our materials and devices in representative environments. So, for example, my students go to NASA to test their samples and devices in the Venus Chamber.
The Venus Chamber.
Located at NASA Glenn Research Center.
My mind just went on a reverie. I have to bring myself back to space. Please go on.
Yeah, so the Venus chamber, I know, the Venus chamber actually simulates the pressure, temperature, and chemistry that one might find on Venus. And so it's a great platform to simulate what the electronics will go through. And that helps us really get a sense for how well the technology will work, really validate our hypothesis that these materials will function for extended periods of time. So that's one way we actually help mature the technology. Also, my students work with companies out of Moffett Field, one in particular, Boreal Space, who's working with us to do suborbital launch of our technology. So we're going to send our materials 62 miles.
Oh, that must be super exciting.
Yeah, launching on a rocket, and we'll see how the packaging, how does everything hold up in the shock vibration aspect of things. So to get back to your question, how mature is this technology? When will we see it? I hope that we'll see it one day through the data that we get from our experiments, but I would say it's still pretty much early stage.
The space industry is fascinating. One of the things about the space industry is, as you know well, in the 60s and 70s, there was a boom of interest. There was engineers working on it. And I must say that in my generation, and I'm a 50-something-year-old guy, for those of you who need to know that, there was actually a dearth of people working on space. It wasn't a national priority. A lot of us went into medicine or biology or chemistry or computer science where there was a revolution happening. And now I notice that there's this new generation of activity in space. Our generation was kind of a lost generation. I have a father-in-law who's a thermodynamic engineer, worked on rockets in the 60s, and he's been called out of retirement several times because his expertise is needed. So tell me about the industry and your take on how things are looking in terms of, is there going to be a real industrial opportunity for economic value in space?
Right. And I think that is the open question. Number one, it's an exciting time to be an aerospace engineer. And I like to think of it as the new renaissance, right? The new space age. And what we are seeing is agencies, even outside of NASA, right? So moving outside of the government sector into the private sector. We're seeing companies like SpaceX starting to send things to the International Space Station. So and also sending, payloads over and over again, reusing them.
Yes, those pictures of those rockets coming back down and standing up just are spectacular.
It's spectacular, an amazing engineering feat to launch and relaunch a rocket. And so our access to space is going to become more and more available to us, and it's also going to push the costs of sending things to space down. So I think it's an amazing opportunity to think about, what can we place in space? Will we build things in space, right? Will we harness and mine things in space? Of course, there's a lot of open questions about that. There's a lot of policy and ethics. That's the conversation right now. But it certainly is an exciting time.
You must have contact with the folks at these companies like SpaceX and others. It seems like every billionaire has their own space company. Forgive me, billionaires out there. I don't want to lose that segment of our listenership. But for these companies, do you have a sense of what their priorities are in terms of the kinds of materials they would love for you to produce? General robustness, of course, I'm sure they care about. Size, you mentioned very early in our discussion. What are the things that they care about, and do you know how they think they're going to make money?
Yeah, so I think manufacturability and cost is also, you want to have the performance and also have the cost benefit as well. And so that's another engineering challenge in addition to the size and robustness that was mentioned previously.
Do your materials look pretty good in terms of their manufacturability compared to silicon? Are we going to have extraordinary engineering measures, or do it look like you'll be able to manage them?
Actually, we use use the same facilities that silicon technology utilizes. So we use clean room facilities. They're very, very similar.
So everybody wears their
ways.
suit and
Yes.
no dust allowed.
My students wear bunny suits. I wore a bunny suit when I was a student.
Bunny suit while walking to the Venus chamber.
Exactly. And so I don't think it's a giant leap, but a lot of the materials that we develop are pretty new, so they are on the costly side.
Yes.
They're not as cheap as silicon, so I think that's one of the questions, open questions that we have to really grapple with. But as we begin to mature the technology, maybe the cost will go down and things will become more mainstream. So I think those are some of the things that companies think about.
Yes. The gallium nitride and these new materials that you're working on, you described them earlier as a little bit like ceramic. And so that immediately got me worried about vibration and fragility. And I suspect that you have to worry about all of these things.
Yeah, that's a great question. So indeed, ceramics are known to be brittle and fracture very easily. But what's interesting is when you manufacture them on the nanoscale, they're very, very tough. And so their properties actually become more resilient when you manufacture them at the nanoscale. Also, when you have teeny tiny components, they're not as susceptible to shock because they have low mass.
Right.
So they're able to survive
Less
high
inertia.
shocks. That's right.
You have been listening to the Future of Everything podcast with Russ Altman. I want to remind you that the Future of Everything started out as a radio show on SiriusXM, so you'll hear references to that. Now it is 100% podcast, but we still have access to the great shows that we taped with SiriusXM. There are more than 215 of them, and they cover an extraordinary range of topics. If you're enjoying the podcast, please consider subscribing or following so that you can be alerted to every new episode and never be surprised by the future. Maybe tell your friends about it too. Definitely consider rating and reviewing it. That helps us grow, improve, and also spreads the word. You can connect with me on Twitter at RBAltman and with Stanford Engineering at StanfordENG.